In this video, we will discuss tool life and tool materials. Cutting life of tool expressed in time. Time period measured from start of cut to failure of the tool. Cutting tool technology has two principal aspects: tool material and tool geometry. The high forces and temperatures during machining create a very harsh environment for the tool. If cutting force becomes too high, the tool fractures. If cutting temperature becomes too high, the tool material softens and fails. Continual wear of the cutting edge ultimately leads to failure. Three main causes of tool failure. Fracture failure. This mode of failure occurs when the cutting force at the tool point becomes excessive, causing it to fail suddenly by brittle fracture. Temperature failure. This failure occurs when the cutting temperature is too high for the tool material, causing the material at the tool point to soften, which leads to plastic deformation and loss of the sharp edge. Gradual wear. Gradual wearing of the cutting edge causes loss of tool shape, reduction in cutting efficiency, an acceleration of wearing as the tool becomes heavily worn, and finally tool failure in a manner similar to a temperature failure. This is the Taylor tool life equation, where V cutting speed, M/min, T tool life, min. Value of N is relative constant for a given tool material. Value of C depends on tool material, work material, and cutting conditions. The three modes of tool failure allow us to identify three important properties required in a tool material: toughness, hot hardness, and wear resistance. Toughness. To avoid fracture failure, the tool material must possess high toughness. Toughness is the capacity of a material to absorb energy without failing. It is usually characterized by a combination of strength and ductility in the material. Hot hardness. Hot hardness is the ability of a material to retain its hardness at high temperatures. This is required because of the high temperature environment in which the tool operates. Wear resistance. Hardness is the only important property needed to resist abrasive wear. Wear resistance in metal cutting depends on more than just tool hardness, because of the other tool wear mechanisms. Other characteristics affecting wear resistance include surface finish on the tool. A smoother surface means a lower coefficient of friction, chemistry of tool and work materials, and whether a cutting fluid is used. Now we will discuss different tool materials. 1. High-speed steel, HSS. Composition: carbon, 0.8 to 1.5%, chromium, around 4%, tungsten, 18%, vanadium, 1 to 5%, cobalt, sometimes added to improve hot strength. Properties: good toughness and wear resistance. Retains hardness up to 600 degrees C. Easy to machine and sharpen. Applications: general-purpose tools like drills, taps, reamers, and milling cutters. Low to moderate cutting speeds in steels and non-ferrous materials. 2. Cemented carbides. Composition: tungsten carbide, WC, particles bonded with cobalt. Properties: high hardness and wear resistance. Retains hardness up to 800, 1000 degrees C. Brittle, requiring careful handling. Applications: high-speed machining of steels, cast irons, and non-ferrous metals. Turning, milling, and drilling applications. 3. Ceramics. Composition: aluminum oxide, Al2O3, or silicon nitride, C3N4. Properties: extremely hard and wear-resistant. Retains hardness up to 1200 degrees C. Low toughness and poor impact resistance. Applications: high-speed machining of hardened steels and cast irons. Abrasive materials in dry or semi-dry conditions. 4. Cubic boron nitride, CBN. Composition: synthetic cubic crystalline form of boron nitride. Properties: second only to diamond in hardness. Excellent thermal stability, 1400 degrees C, and chemical resistance. High wear resistance. Applications: finishing operations on hardened steels, cast irons, and superalloys. Ideal for cutting hard and abrasive materials. 5. Polycrystalline diamond, PCD. Composition: micron-sized diamond particles sintered onto a carbide substrate. Properties: extremely high hardness and wear resistance. Poor thermal stability, not suitable for ferrous materials. Applications: cutting non-ferrous metals, aluminum, copper, composites, and ceramics. High-precision machining in aerospace and automotive industries. Cutting fluids are substances applied to the interface of a cutting tool and the workpiece during machining processes to improve performance, reduce wear, and enhance the overall efficiency of the operation. These fluids can serve several purposes, including cooling, lubrication, the removal of metal chips or debris, and corrosion protection. There are different types of cutting fluids. Examples: water-based fluids, soluble oils, synthetic fluids, semi-synthetic fluids. Oil-based fluids, straight oils, pure oils, additive-enhanced oils, include additives like sulfur, chlorine, or phosphorus. Gaseous fluids, compressed air or inert gases. Solid lubricants, graphite or molybdenum disulfide. Thank you. Thank you for watching this video.